Hey there, everyone. Nidal here from the OpenAir Collective. Very excited to bring you this Violet prototype tour with Professor Tao Wang from Zhejiang University. Violet is a new open-air mission soon to be launched in 2020 that you're going to be hearing a lot more about over the next few months. But in short, just to give you a teaser right now, Violet is going to be, we believe, the world's first open-source, peer-produced direct air carbon capture machine, or DACC machine. DACC is a technology that chemically removes carbon dioxide from the ambient air. In the future, it has the potential to do so at rates that are up to 1,000 times more efficient than trees, according to a recent National Academy of Sciences study, making it potentially a really important part of how we address the climate crisis. So our goal for Violet is to release the designs for a miniaturized open-source DACC out into the world under an open-source license, and then build a global community of contributors from all kinds of different backgrounds who can collectively focus their time, attention, and talents on solving some of the key technical and cost barriers that currently limit DACC's potential. As a community, we also want to explore and create new ways of applying DACC in the real world, and we want to do both of these things at an accelerated, rapid rate that matches the time frame of the climate crisis itself. And Professor Tao Wang is a huge part of this effort. He's been involved with the project from its very earliest concept development. So Tao is kind of, for lack of a better term, OpenAir's DACC technical guru. We'll explain why in a second. And more importantly, his research and development that he and his lab have been doing are really the basis, technically, of what will be the Violet prototype. And once we're up and running, Tao also is going to be offering critical guidance on what types of problems we should be focusing our attention on as a community. Some background on Tao. He is one of the world's leading direct air carbon capture moisture swing research engineers. He's published dozens of articles in different journals on the subject. He completed his postdoctoral research with Dr. Klaus Lochner at Columbia University about a decade ago. Dr. Lochner is universally regarded as really the inventor of direct air carbon capture, and he remains one of the leading and seminal figures in the field today. Today, Dr. Wang is a full professor at Zhejiang University, one of China's top technical university, where he works in the State Key Laboratory for Clean Energy Utilization and runs a group with himself and his grad students focused on technical improvements and research in direct air carbon capture. And the work of his group has achieved some really significant improvements in the field. And for that, they were named as one of the finalists for the NRG COSIA Carbon X Prize, a prestigious global award focused on carbon removal solutions. So in just a minute, we're going to join Tao in his laboratory in the University of Zhejiang, where he's going to give us an overview of a prototype of a miniaturized DACC unit that's similar to what the Violet unit is going to consist of. So he's going to start by giving you just a component-by-component view of this machine itself. I think it'll be helpful for those of you who are new to this field. Before we hear from Tao, I'm just going to give you a little bit of a heads up on what you're about to see in the laboratory and lay out some key concepts that Tao's going to go into in greater depth. First, what you're looking at right now is an image of the prototype in Tao's lab of the direct air carbon capture unit that he's about to give us a tour of. One term that you should know and that you're going to hear from Tao is moisture swing. There are different types of DACC technology that capture and release carbon based on different factors. Moisture swing technology does so based on the humidity of the ambient air. As Tao will demonstrate, when the air is dry, CO2 is captured. When it is wet, it is released. In the lab, Tao is going to show us three main pieces of equipment. The capture unit is where the sorbent is stored, and the sorbent is the material that both absorbs and releases the carbon dioxide. You will also see a miniature sealed greenhouse. Greenhouses are an important potential application for direct air carbon capture because carbon dioxide can be pumped into them, and that can accelerate and improve the growth of plants inside. In this case, flowers. But greenhouses are also just excellent, easy ways to measure the impact and efficacy of a DACC machine, and that's what Tao uses in his lab. The final pieces of equipment that you're going to see relate to measuring and monitoring. Tao uses an infrared gas analyzer to detect how much carbon dioxide is in the greenhouse, and this information is displayed on a monitor of a laptop using the software that comes with that infrared analyzer. And one last key thing I want to stress is the unit that Tao is about to show us is not the Violet unit, but rather what the Violet unit is based on. A couple of key differences. When we talk about Violet, we're really talking about that capture unit, and it's also going to include some inbuilt monitoring and measuring tools. However, they're going to be a bit different from what Tao uses in his laboratory, which are a little bit more fancy and expensive than what we require. So after Tao wraps up his component overview, He's then going to get into some of the very specific problems and challenges that his lab is currently working on, improvements that he would like to see to the prototype and, critically, to the sorbent that it uses. These challenges we can work with Tao on in the future and have those be the basis of some of the projects that we work on as a community. And then to wrap up, Tao is going to get into some of the specific DACC CO2 applications that he's most excited about and that he's focused on. So these are things that the CO2 from direct air carbon capture can be used for in the real world. So with that, I'm going to let Tao take over from his laboratory at Zhejiang University. I hope you enjoy.
Hello, welcome to our lab, the lab of direct air capture. And this is one of our labs which we show how the direct air capture works. Yeah, now you see the solvents are in this kind of very interesting frame. And then actually at first we don't know how to, where to put the solvents. So we make a part like this, yeah, to fix the solvents. And this they are layered like this so that we can increase the resistance when the wind flows through it. Yeah, but generally we develop different kind of these solvents. There are like, if you read our paper, you will know there are different kind of resins. There are resins inside, and then when we make the solvent like this kind of sheet, actually we can cut it to different shapes, and then we fix it on this frame. So yeah, the resins are grinded into fine powders, and then they are embedded into this kind of membrane. These are like the PE or PP, or you can choose different kind of polymer supporter for the resin powder. So we hope to increase the capacity and the kinetics. Yeah, and but for the moisture swing process, we also wish to increase the environmental tolerance. That is, can the material work at a relatively high environment? So if you look at the screen, we have a screen here. Yeah, so this is the chemicals, the solvents reaction with the CO2. So for us, we hope to, to modify the functional group so that we can increase the humidity tolerance. So we can let it work at higher humidity, like 50% or 60% of the humidity. And we also needed to dissolve it when we spray water on it. So that's the solvent work, the material development on the functional group. And the second kind of work on the solvent development is the microstructure design. When we capture CO2, we need the CO2 diffused from the air to inside the solvents. We need to design channels for the molecules diffusion. Then we are we're optimizing the microstructures, the microchannels inside the resin. So when we talk about the microchannel, it's kind of a channel in the size of smaller than a micrometer, the nanometers. When we talk about the exposure surface area, actually, we mean not only the micropores inside the resin, but also the structure design. Like when we expose the solvent to the air, how can we let the air diffuse quickly into the solvent module? So as I said, for the moisture swing, it's a very interesting phenomenon. We need dry atmosphere, and on the other hand, we need the moisture to recycle the solvent or recycle the CO2. So in the lab now, what we're demonstrating are two units. The one unit is a capture unit. So this is the capture unit. You can see that we fix the solvent here, and then we study how to separate, how to design the absorption process and the desorption process, right? So we use this kind of structure, yeah, which they can unfold, Yeah, if you increase it. Yeah, so if you need to capture the CO2, you will lift it up, yeah, so that the wind can flow through the solvent, right? And
Okay.
like after a while, like maybe half an hour to 1 hour, wind capture all the CO2 is fully loaded. This part will unfold and will be moved to the chamber below. Yeah, this chamber below. Yeah,
Yep.
so it will move to the move into the chamber, and as this is a as this is fully loaded with CO2, we spray water. Maybe you can find some nozzles. Yeah,
Gotcha.
the water will be sprayed from here.
Ah,
Yeah,
okay.
here. Yeah, so that all the solvent will be wet. It will be wet,
Gotcha.
and the CO2 will be released out from the system. And this chamber actually will be closed at that moment. It is sealed and closed, and all the CO2 will be pumped from the tubing to this greenhouse. This is a beautiful device. It simulated the greenhouse. Yeah, we have the green plants inside it. Yeah, and actually the green plants can capture the CO2, can utilize the CO2 quickly. Yeah. And you see that we use this instrument to monitor the CO2 concentration. This is an infrared gas analyzer. Question. So, how frequently the moves is related to the kinetics. So for this material, it's already loaded. They need about 1.5 hours for capture and another 1 hour for the desorption. So generally, we need about 3 hours for one cycle. So in a day of 24 hours, we can do 8 cycles. So that's the reason why we're studying how to increase the kinetics. Yes, and I also like your idea about the open source. I really hope the researchers and the engineers can work together to improve the design, and they can also give us feedbacks about the material, and then we can work together with other material scientists to improve the solvent. Then we can have the direct air capture unit with a lower cost. And I think that is what that is our aim for to fight the global warming. You see this unit, yeah, it's a prototype, but I think it's the origin. Yeah, if you see here, yeah, so the prototype is the origin. Yeah, right? But from the origin, we can see how can we reduce the cost, right? How can we reduce the cost? Like if you look at the machine again, you will know what's the most expensive part. It is not the solvent, it's not the chamber, but it is the machine. It's the
Yeah.
moving part. The moving part is the most expensive, yeah, part. So as I said, this is the previous design, not the current design. Our current design is, can we remove the moving part? What we are doing is to reduce the absorption time or increasing the kinetics of the capture process. And we said we
Gotcha.
design the microstructure, optimize the structure design, optimize the microchannels inside the resin. These are used to increase the kinetics. Yeah. So currently, the absorption time can be reduced to like 10 minutes, and the half time is 5 minutes. Then the total absorption time is 10 minutes. Then if we have another 10 or 20 minutes for the desorption, then the total cycle will be controlled inside 1 hour. And the last question, the very last thing is the very important. So you said a ladder system, And my question is, what means a larger system? For this unit, do we need to make it 1,000 times larger, or we just need 1,000, quantities of this unit? Yeah. Yeah. That's the first thing is about this design. Can we optimize the flow field of this the solvent framework? Yeah, that is what we are, very interested in. Yeah. For the current machine, we only have one group of this solvent. But what if we have more, like 16 groups of this solvent? How can we, to arrange these the solvents? And the other thing is that we talked about a dehumidifier. Yeah. Of course, our aim is to develop the solvents which have a higher humidity tolerance. But currently, we need to know, if we really need to capture more CO2 in the humid atmosphere, so maybe we need a dehumidifier. And the dehumidifier maybe need energy and need material, need some like the silica gel to remove the moisture. Then the material is expensive, and at the same time we need the high energy input. So how can we decrease this the material requirement and energy requirement? It's not directly related with the solvent, but it is the very important part of the moisture swimming process. So if we have a dehumidifier, how can we optimize this? And I think this is the engineers can help us to improve it. We hope to remove the moving part and then fix them into a closed chamber, and then that we need a pretreatment for the inlet air. So the dehumidifier will be in the pretreatment position. Yeah. So to remove the humidifier and then into the chamber for absorption. For the moisture swimming process, actually, at first we think we do not need any kind of electricity. What do we need this now? It's water, right? We need water. Or we can use the warm water, like 40-degree or 50-degree water. But once we have this unit, we found that we need electricity. We need electricity to move this part, move the solvent, or we need electricity to pump the CO2 into the chamber, or pump the CO2 through the solvents. So that's the reason why I said we need to optimize the structure so that we can decrease the electricity requirement, the electricity for pumping the air. Yeah. Actually, we are thinking different kind of ways to increase the partial pressure of the CO2. Then that's very important. And so we're starting like, how about the liquid, the chemical solvent? Generally we use the chemical solvent to capture the CO2 from flue gas, and their concentration is like 5% to 15%. And this kind of chemical solvent can increase the concentration to 100%. But at that moment, you need high temperature heat. So that's a challenge. Yeah. And if you need pure CO2 from the air, you need high temperature heat or much more electricity. Technically, we can do that. We can increase the partial pressure. Yeah. But we need to study how to decrease the energy cost. So that is what we can think from this origin.
Yeah.
Yeah. So the CO2 can be converted to different kind of products. With electricity and water, we can electrolyze the CO2 and the water to hydrogen and the CO, and then we get the syn fuel. Yeah. So that syn fuel is kind of a zero emission syn fuel. What we are studying is the green concrete. Yeah, the green concrete is from the solid waste. It's kind of industrial solid waste like the slag, the fly ash. Yeah, this kind of waste and the CO2. So the alkaline material inside this solid waste can react with the CO2 and form a kind of the calcium carbonate, which can increase the strength of the material. And generally, when we talk about building the blocks, and we need the concentrated CO2 to diffuse into the blocks to increase the strength. But what we are developing now is kind of porous blocks. They have a lot of holes in the pores, so that we found out the CO2 from the output of direct air capture can be utilized to do the concrete curing, and that's very exciting.